Hello, in this video I'll be working through our Day 2 homework assignment, which is a review of functions and trig. In this first problem, we're going to evaluate the composite functions f of g, g of f of f, and g of g for the indicated values of x. So let's start with this problem right here. We want to find f of g of x when x is 1. So we want f of g of 1. I'm going to evaluate this working from the inside out. So I want to find what is g of 1. To find g of 1, I'm going to look for the row for function g, add an x value of 1, and that is equal to 3. So f of g of 1 is equal to f of 3. And to find f of 3, I go to the row for function f, and I'm using an x value of 3. So that is equal to 5. So my final answer here is 5. I'm going to work down this first column. So next I want to find g of f of 1, which is equal to g of, now I find f of 1. So f of 1 is equal to 4. So g of f of 1 is equal to g of 4. Function g at an input value of 4 is equal to 2. Next, I'm finding f of 1. F of 1 is 4, so I want f of 4. F of 4, function f, evaluated at 4, is 2. So f of 1 equals 2. And g of 1, I want to first find g of 1. So g of 1 is 3. And then for g of 3, we will evaluate g at 3. We get 0. So g of 1 is equal to 0. Okay, so let's finish the rest of these up in a similar fashion. When our input value is 2, here we need f of g of 2. G of 2 is equal to 4. So then I want to find f of 4, which is 2. G of f of 2. F of 2 is 3. G of 3 is 0. Next we have f of 2. F of 2 is 3, and f of 3 is 5. And in the last row we have g of 2. G of 2 is 4, and g of 4 is 2. Next column, our input value is 3. So here I want f of g of 3. G of 3 is 0. And f of 0 we don't have in our table. So we actually can't determine the value of f of g of 3. That one we won't be able to do. G of f of 3. Well, f of 3 is 5, and g of 5 is 1. Next we have f of 3. F of 3 is 5, and f of 5 is 3. And then we have g of 3. G of 3 is 0, and g of 0 we can't find from the information given in the table, so we don't know that one. Okay, next we have an input value of 4, so we want f of g of 4. G of 4 is 2, and f of 2 is 3. Then g of f of 4. F of 4 is 2. G of 2 is 4. Then f of 4. F of 4 is 2, and f of 2 is 3. Then g of 4. G of 4 is 2, and g of 2 is 4. For our last column, our input value is 5, so we want f of g of 5. G of 5 is 1, and f of 1 is 4. Then we have g of f of 5. F of 5 is 3. G of 3 is 0. Next, f of 5. F of 5 is 3. F of 3 is 5. And finally, g of 5. G of 5 is 1, and g of 1 is 3. For this next few problems, we're evaluating composite functions using graphs. So number 2, we want f of g of negative 2. You may find it easier to write this using the other notation, f of g of negative 2. And we're going to work from the inside out here. So first we want to determine g of negative 2. We'll go to the graph for g. At an input value of negative 2, the output value is 0. So this is going to be f of 0. Now we want to evaluate f of 0. So we go to function f. At 0, that output value is negative 4. So final answer, f of g of negative 2 equals negative 4. Number 3, f of g of negative 3. So this is f of g of negative 3. We can find g of negative 3 by looking at the graph of g at an input of negative 3. So that gives us an output value of 1. So this becomes f of 1. We go to function f at an input value of 1. Our output value is negative 5. Number 4, we want f of 1. F of 1 is negative 5. So this is f of negative 5. And then we look at the graph of f at negative 5. Output value is 1. F of 1 equals 1. Number 5, g of f of 0. F of 0, function f at 0 is negative 4. So g of negative 4. And then function g at negative 4 is 2. So g of f of 0 equals 2. Number 6, g of f of negative 4. F of negative 4 is 0. So this becomes g of 0. And then g at 0 is 2. Number 7, g of 1. G of 1 is 3. So we have g of 3, and then g of 3 is 5. Number 8, determine an f of x and g of x such that h of x equals f of g of x. So we want to identify an inside function and an outside function. G of x is our inside function, so I'm going to let that be the part of h that is inside the square root. So g of x equals x squared plus 3. And then f of x is our outside function. That's going to be the square root of x. So that when we compose this, f of g of x, if we want to check this, we use g of x as the input for function f. The rule for function f is square root of input. So if we do square root of input, and our input is x squared plus 3, we do get h of x. Number 9, this one is a little more difficult. And one thing we can do, and this will work in all of these cases actually, we can let our inside function be x. And then our outside function is going to look the same as our composite. Because now if we find f of g of x, we're using the rule for f, which is input over input squared plus 1. So input over input squared plus 1. And our input is g of x, which is just equal to x. So input over input squared plus 1. So it's not a very interesting example, but it does work. Number 10, g of x is my inside function, so I'm going to use what's inside the parentheses for that. G of x equals 5x. And then f of x is my outside function, and that'll be ln of x. And so when I compose this f of g of x, my rule for function f is the natural log of input. Natural log of input. And my input is g of x, which is equal to 5x. So that works. Number 11, evaluate sine of 2 pi over 3. So 2 pi over 3 is quadrant 2. Our reference angle is pi over 3, or 60 degrees. And the sine of 60 degrees, or the sine of pi over 3, is square root of 3 over 2. Square root of 3 over 2, and I'm in quadrant 2 where the sign is positive. So that is going to be my answer, root 3 over 2. Number 13, secant of pi. So pi is 180 degrees. That is here, if I'm thinking in terms of like unit circle. And secant is the reciprocal of cosine. So I know the cosine of pi is -1. I want the reciprocal, so 1 divided by cosine of pi. 1 divided by -1, which is just -1. 7 pi over 4, that's 8 pi over 4, or 2 pi, minus 1 pi over 4. So now I'm in quadrant 4. My reference angle is pi over 4. Cosecant is the reciprocal of sine. So I'm thinking, what is the sine of pi over 4? The sine of pi over 4 is 1 over root 2. But I don't want the sine, I want cosecant, which is the reciprocal. So when I take the reciprocal of 1 over root 2, I get root 2. And I'm in quadrant 4, where the sign is negative, so its reciprocal will also be negative. So this is negative root 2. Number 17, secant of pi over 3. So pi over 3, 60 degrees, that's quadrant 1. Secant is the reciprocal of cosine. The cosine of pi over 3 is 1/2. I want the reciprocal of that. So reciprocal of 1/2 is 2, and in quadrant 1, cosine is positive, therefore its reciprocal is also positive. Number 12, cosine 5 pi over 6. 5 pi over 6 is 6 pi over 6 minus 1 pi over 6. So we are in quadrant 2. Cosine is negative in quadrant 2. My reference angle is pi over 6, and the cosine of pi over 6 is square root of 3 over 2. 14. Tangent of 5 pi over 4. 5 pi over 4 is 4 pi over 4 plus 1 pi over 4. So now we're quadrant 3. Tangent is positive in quadrant 3. So I know my answer is positive. My reference angle is pi over 4. Tangent of 5 pi over 4 is sine of 5 pi over 4 over cosine of 5 pi over 4. But in terms of reference angle, I can just find sine pi over 4 over cosine pi over 4. And that's going to be 1 over root 2 divided by 1 over root 2. Or you might just remember that the tangent of pi over 4 is equal to 1. Number 16, tangent of 3 pi over 2. 3 pi over 2 is 270 degrees, right, if we're thinking in terms of unit circle there. And so our tangent is going to be the sine of 3 pi over 2 divided by the cosine of 3 pi over 2. So sine of 3 pi over 2 is -1. Cosine of 3 pi over 2 is 0. -1 over 0 is undefined. 18, cotangent of 11 pi over 6. 11 pi over 6 is 12 pi over 6 minus 1 pi over 6. So we're quadrant 4. Tangent and its reciprocal cotangent are negative in quadrant 4. So my answer is negative. My reference angle is pi over 6. And cotangent is cosine over sine. So cosine of pi over 6 divided by sine of pi over 6. Cosine of pi over 6 is root 3 over 2. Sine of pi over 6 is 1/2. Then you can flip and multiply. We're just going to be left with negative root 3. 19. Find the values of the 6 trig functions at the angle theta. Give exact values. If theta equals arcsine of -4 over 9, that tells me that the sine of theta equals -4 over 9. When you have an inverse, you switch your input and your output. I also know that sine of theta is defined as the opposite leg length over the hypotenuse, opposite over hypotenuse. So if I draw a right triangle to use as a reference here, I'm going to label the opposite side 4 and the hypotenuse 9. Okay, now we can use Pythagorean theorem to solve for the remaining side. So that's going to be the square root of 81 minus 16, or square root 65. Now we have arcsine of negative 4/9. If sine theta is negative 4/9, then theta must terminate in quadrants 3 or 4. But arcsine is only going to give us a theta value in quadrants 1 or 4. So I know I'm working in quadrant 4. This has to be an angle that terminates in quadrant 4. And in quadrant 4, cosine is positive, sine is negative, tangent is negative. So I'm going to keep that in mind here as well. So I already have sine theta is negative 4/9. Cosine theta, that's my adjacent length over my hypotenuse, so root 65/9. Tangent theta, that's going to be the sine over the cosine, so negative 4 over root 65. Then we can do our reciprocals. Cosecant theta is negative 9/4. Secant theta, 9 over root 65, just the reciprocal of cosine. And cotangent theta, negative root 65/4. Number 20, theta equals arctan root 3. Now we can approach this a couple different ways. This is actually a special angle. I recognize root 3 as one of my special trig values. If theta equals arctan root 3, I know that tan of theta equals root 3. So you might just remember what angle theta has a tangent equal to root 3. We can also think of the number root 3 as root 3/2 divided by 1/2. When you're dividing fractions with the same denominator, the denominators just cancel out. So where is sine equal to root 3/2 and cosine equal to 1/2? That would be at a reference angle of pi/3. So we could complete the problem knowing that theta is pi/3. We could also use the right triangle approach. All right, so here's our angle theta. Tangent is opposite over adjacent. So if I think of the number root 3 as a fraction, it's root 3/1. And then I can use Pythagorean theorem to get the remaining side. That's going to be the square root of leg squared plus leg squared. So leg squared plus leg squared would be 1 plus 3, or 4. Square root of 4 is going to give me 2. Okay, so the hypotenuse is 2. And I can list out my 6 trig functions. The sine of theta would be opposite over hypotenuse. And I probably should have checked my sines as well. If tan theta is root 3, positive root 3, I know that tangent is positive in quadrants 1 and 3. But arctan is only defined in quadrants 1 and 4. So theta must be in quadrant 1. Quadrant 1, all of our 6 trig values are going to be positive. So sine theta equals root 3/2. Cosine theta is going to be the adjacent leg over the hypotenuse, or 1/2. Tan theta, opposite over adjacent, or we already know tan theta is root 3. And we can look at our reciprocal trig functions. Cosecant theta is just the reciprocal of sine, 2 over root 3. Reciprocal of cosine is secant, so secant theta equals 2. And then cotan theta, 1 over root 3. 21, theta equals arc cosine x over 2. That tells me that the cosine of theta is equal to x over 2. So I'm going to draw a right triangle to use as reference. And if the cosine is x over 2 and cosine is adjacent over hypotenuse, then my third side for my triangle would be the square root of 4 minus x squared, hypotenuse squared minus leg squared. Since x is unknown, we don't know if it's positive or negative. For this one, I don't know which quadrant I'm working in. So we're just going to stick with sine theta being the opposite over hypotenuse, cosine theta, x over 2, adjacent over hypotenuse, tangent theta, opposite over adjacent, and then our reciprocals. Cosecant theta, 2 over square root 4 minus x squared, secant theta, 2 over x, and cotan theta, x over square root 4 minus x squared. Number 22, solve for x. Let's start by adding sine x to both sides of this equation. So I get 2 sine x plus root 2 is equal to 0. And then we're going to subtract root 2 and divide by 2. So we get sine x equals negative root 2 over 2, which is the same as negative 1 over root 2. And that is one of our special trig values. So if we're thinking in terms of unit circle, where does the sine equal negative root 2 over 2? Our reference angle is pi over 4, but sine is negative in quadrants 3 and 4. So I have pi over 4 as a reference angle here and here. This is going to be 5 pi over 4. 4 pi over 4 plus another pi over 4. This one here, it's 2 pi minus pi over 4. So 8 pi over 4 minus 1 pi over 4 is 7 pi over 4. Now these are just the two solutions between 0 and 2 pi. But we're asked to find all solutions. So it's 5 pi over 4 plus all of the corresponding solutions in other cycles. And my period here is 2 pi. So to get to the next corresponding solution in the next cycle, I would add 2 pi, and then I would continue to add multiples of 2 pi. Or I could subtract multiples of 2 pi. So plus 2 pi k, where k is an integer. And then we also have 7 pi over 4 as a solution, again, plus 2 pi k. I've already defined k, so I don't need to do that again, but this is our solution here. Number 23, 3 tan squared theta minus 1 equals 0. So we could solve this by factoring. We can treat this as the difference of two squares and factor. If we did that, we'd have root 3 tan x plus 1 and root 3 tan x minus 1 equals 0. That's typically not the way students approach this one, which is okay. We could also just add 1 to both sides and divide by 3. If you approached it that way, you would have tan squared x is equal to 1/3, and then you can take the square root of both sides, but there you have to remember that tan x could be plus or minus the square root of 1/3, or 1 over root 3. So either way, we get these two kind of anchor solutions, plus or minus 1 over root 3. And that is one of our special values, unit circle values as well. So where does tangent equal 1 over root 3? Well, 1 over root 3 we can think of as 1/2 over root 3 over 2. When you're dividing fractions with the same denominator, the denominators just cancel out. So where is sine 1/2 and cosine root 3 over 2? That occurs at pi over 6. So thinking in terms of unit circle, we have solution at pi over 6, and we have another one over here, and we have another one here, and we have another one here. So pi over 6, now if I just add pi to that, I get the next solution. If I add pi again, I get the next solution, and so on. So I've got pi over 6 plus multiples of pi this time, so plus pi k, which makes sense because the period for the parent tangent function is pi, not 2 pi. And then over here we have 5 pi over 6, or we could also say negative pi over 6. In any case, if we start at 5 pi over 6, or if we start at negative pi over 6 and we add pi, we keep getting more and more solutions, or if we subtract pi. So we We could say 5 pi over 6 plus pi k, or I could say negative pi over 6 plus pi k. If I have pi over 6 plus pi k and negative pi over 6 plus pi k, then the simplest way to express this is just going to be plus or minus pi over 6 plus pi k. And number 24, so this is in the form of a quadratic function. If we think of sine x, if we just substitute that for, let's say, w, then this becomes 2w squared minus w minus 1 equals 0. This is in the form of a quadratic equation. So we could solve this quadratic by factoring, possibly, or using the quadratic formula. Let's see if it's factorable. 2w squared would be 2w times w. The only way to get 1 here would be 1 times 1. Or maybe I shouldn't say the only way, but the most likely way. 1 and 1. And let's see if we can get the signs to work for us here. We want a negative 1w in the middle. So I want the 2w to be negative and the 1w to be positive. So that is factorable. And my solutions here, 2w plus 1 equals 0, or w equals negative 1/2. And then over here, just w equals 1. But remember, w really was just a placeholder for sine x. So I have sine x equals negative 1/2, or I have sine x equals 1. And now we're going to solve from there. So where does sine x equal negative 1/2? Well, sine x equals positive 1/2 at pi over 6. Negative 1/2, sine is negative in quadrants 3 and 4. So we're down here. Reference angle pi over 6. So 6 pi over 6 plus pi over 6 is 7 pi over 6. And then this is 12 pi over 6 minus 1 pi over 6, or 11 pi over 6. 11 pi over 6, or we could just say negative pi over 6. Okay, I guess an equal sign isn't appropriate there. But we could say, we could name that angle either as 11 pi over 6 or as negative pi over 6. And then we want to add the period, so add 2 pi to get corresponding solutions in subsequent cycles. So I have 7 pi over 6 plus 2 pi k for some integer k. I have 11 pi over 6, or we can say negative pi over 6 plus 2 pi k. And then we still need to come back over here and solve this. Where does sine x equal 1? Sine x is 1 at pi over 2. So I also have pi over 2 plus 2 pi k.